Hi, I'm Sampo Pyysalo, and I have the pleasure of presenting our work titled Wikibert Models, Deep Transfer Learning for Many Languages. As background, as I'm sure everybody in this audience knows, deep neural language models such as BERT have had a great impact in natural language processing recently, advancing the state of the art in many tasks. Now, these models are usually introduced primarily for English, with a lot of other languages being considered more or less as an afterthought, as part of massively multilingual models that may include 100 languages or more. Additionally, many languages may not be covered at all. It's also well known that monolingual language models generally outperform massively multilingual models, which has been termed the curse of multilinguality. Additionally, data preparation and language model pre-training are challenging, and differences in these aspects make comparison between language models difficult. In this work, we hope to address some of these issues. We first introduce a fully automated pipeline for creating monolingual BERT models from Wikipedia texts. We then create BERT models for 42 languages. We term these the wikibert models. Finally, we perform a comparative evaluation of these models against Google's multilingual BERT or mbert model on closed task as well as on universal dependencies parsing. As data, we draw primarily on Wikipedia. At the moment, Wikipedias exist for more than 300 languages, and they range in size from 6 million articles for English to just a few hundred for the smallest Wikipedias. We additionally make use of the universal dependencies data. The Universal Dependencies repository currently includes tree banks for more than 100 languages, ranging for over 1 million tokens for the largest tree bank to some thousands for the small ones. Specifically, we use UD version 2.3 tree banks that have train, development, and test sets and include text. This limits our study to 65 tree banks in total. Looking at our source data in terms of tokens, we get more than 2.7 billion tokens from the English Wikipedia, whereas for the smallest language included in our study, we get just 18 million. Looking at some of the Nordic languages, we have some 360 million for Swedish, about 100 million for Norwegian and Finnish, and slightly less than that for Danish. This great range in the amount of training data or pre-training data available naturally has a substantial impact on the models that we train. Next, briefly on the methods and tools used in our pipeline. We use the wiki extractor tool to extract clean text from a Wikipedia database dump. We use UD-pipe, the UD parser, for sentence segmentation and tokenization. We use the LangDetect library for language identification. The language ID in this library is based on character engrams. For subword vocabulary generation for the BERT model, we use sentence piece, an implementation of byte pair encoding. And finally, in our evaluation, we use the UDify parser, which is a state-of-the-art neural parser that accepts UD data. Here's an outline of the pipeline that we introduced. As a starting point, we have a Wikipedia database dump. We then perform text extraction using wiki extractor. The data is then segmented using UD pipe, creating sentence split and tokenized text. That text is then filtered using language detection as well as a number of heuristics. This eliminates, for example, documents that are not primarily in the target language of the Wikipedia, as well as documents that have too little natural language, so things like just tables instead of sentences. This initial part of the pipeline produces filtered and sentence split documents, which are used in two further parts of the pipeline. First, here on the left, we have a vocabulary generation stage, where we first sample a subset of documents, because Sentence Piece doesn't want to process enormous corpora. And we do BERT basic tokenization so that the tokens that the Sentence Piece gets as input agree with the BERT implementation. We then run Sentence Piece to generate a vocabulary that is converted. This is just a format conversion. It's then converted to a word piece vocabulary for BERT. This vocabulary is then used together with the filtered sentence split documents for example generation, and these examples are then entered as input into the pre-training process, which generates a BERT model. So we have three outputs, so to speak, from this process, which can be used separately or independently of the model. So in addition to the model, we have the clean, filtered, segmented documents, and we have a vocabulary that can be used also with other models. So next, a few technical details. We generate cased vocabularies, so separating lower and uppercase characters of 20,000 words for each of the languages. We pre-train BERT following the process introduced by the creators of BERT. We train for 1 million steps. We use the default settings for example generation, including full word masking, as well as the optimizer settings suggested in the original work introducing BERT. For pre-training, we use NVIDIA V100 GPUs with 32 gigabytes of memory. We use 4 for the initial training stage with batch size 140, and for final training with the full maximum sequence length of 512 word pieces, we use 8 GPUs with a batch size of 20. The total pre-training time in terms of wall clock time for each of these models is a bit under 2 weeks. To evaluate the models, we compare the performance of each of the wikibert models to Google's multilingual BERT, and we evaluate on both a close test as well as on the UD parsing task. For UD parsing, the wikibert model or nBERT model offer a starting point for fine-tuning, whereas in the close test they are used as is, so in an intrinsic evaluation setting. We note that nBERT is comparable to the wikiberts in terms of its source data. It's trained exclusively on Wikipedia data, as well as the pre-training setup. So this allows us to assess the trade-off between mono and multilingual training. For the closed test, the setting mirrors that of the BERT pre-training masked language modeling objective. So we randomly mask 15% of sentence words and see if the model is capable of predicting those words correctly. We test this on the first 1,000 sentences of a given length from the training data of the UD tree bank for each language. And we evaluate simply using one best accuracy. That is, we check if the word that was predicted by the model is exactly the same word as it was in the source sentence. Now these are the closed test results. There's a lot of numbers behind this, and I won't go into too much detail on them. You can, of course, find all of that in our paper. But just to make a few observations. First, the wikibert model outperforms the mbert model for all the languages considered here, except for Japanese. The wikibert models average 39% accuracy versus 24% for mbert, so they show quite a substantial advantage over the multilingual model. Looking at the highest absolute differences between the multilingual and the monolingual model, we find at the top Vietnamese, Hindi, Greek, Persian, and Indonesian, which may suggest some vocabulary representation issues in mbert. Second, our extrinsic evaluation is on UD parsing, so dependency parsing as a downstream task. Here we initialize the parser with the BERT model, either a wikibert or mbert, then fine-tune on the UD training data and evaluate on the UD test data. Evaluation for UD parsing uses the standard label detachment score metric. And for the languages with multiple tree banks in UD, we just report the average over the label detachment scores of the tree banks. Here are the UD parsing results. Again, I won't go over them individually, but rather make some observations. So here the wikibert models also outperform mbert for most of the languages, averaging 87% label detachment score versus 86 for multilingual BERT. However, the results are much more mixed than in the closed test. So there's small differences only. And in 12 out of the 42 cases, the multilingual model actually achieves higher performance than the monolingual one. And there's very large differences in baseline performance here, with results for small tree banks tens of percentage points below those for large tree banks, which may in part obscure the effects on results. So for this reason, we looked at these results also in terms of the relative change in loss, and we plot that against the pre-training data size, shown here on a logarithmic scale. Again, I refer to the paper for the full detailed results, but note that for English, which has the largest Wikipedia, the results for the wikibert model and the multilingual model are effectively identical. For languages with comparatively small Wikipedias, performance for the monolingual model is generally not better, suggesting that languages with small Wikipedias may benefit from the support that they get from multilingual data. Additionally, closely related languages with comparatively large Wikipedias may still benefit from multilingual training. But we do observe a kind of potential sweet spot here for languages with Wikipedias of middling size, that is, some hundreds of millions of tokens. Coincidentally, Finnish happens to be here the language that benefits most from monolingual as opposed to multilingual training. In conclusion, we have in this work introduced a fully automated pipeline for creating BERT models from Wikipedia, and we applied that pipeline to create 42 monolingual models trained using a process that mirrors the pre-training of multilingual BERT. Many of these models cover languages that did not previously have a dedicated monolingual model, and we hope that the ones that do can serve as a kind of baseline for checking that your monolingual model is in fact outperforming one of these trained only on Wikipedia. We found that the wikibert models outperform multilingual BERT in a closed task for all languages except Japanese. We do not yet have an explanation for this outlier. We also evaluated UD parsing, finding mixed results that indicated effects from Wikipedia size and support from related languages that favored multilingual training. All of the tools and models introduced in this study are freely available under open licenses from the URL shown here. Finally, looking a bit into the future, we're currently working on very large generative language models targeting primarily Nordic languages and perhaps more. Turku NLP is part of a pilot project on the pan-European supercomputer LUMI, which will start in December. And we are very much open to collaboration, and do get in touch if you're interested in this type of work. Our thanks to the Academy of Finland for their support of this work, as well as to CSC, the Finnish IT Center for Science, for their very generous computational resources. And finally, thanks to you for watching.